Okay, so I left you off with this example. I hope that you worked it and just didn't push play on the next one just to get a free answer again. But if you did solve it, try to double check your answer. See where you messed up, even if you did at all. So I am told I have to start with this stupid thing over here to the left. I have to start with this 1-bromo, 1-methyl cyclohexane. The good news is that they didn't complicate things and give me solid and dashed wedges. So here in the beginning, it looks like they don't care about stereochemistry, right? Otherwise, they would have done it. So there we go. Well, truth of the matter is, this bromo group, just to kind of review another video that we did before, this bromo group should not be equatorial. I know that. No equatorial bond there. So that means that this thing has to be axial. That also means that this methyl group has to be equatorial. So if I do want to draw it, they're actually giving me enough information here. This first carbon of the cyclohexane ring has an axial bond and an equatorial bond, right? So this CH3 group and this bromo group has to be in a certain location. Otherwise, things like elimination and stuff is not going to work. And we might need elimination, so we want to play it safe. So bromo cannot go in equatorial. Bromo has to go axial here, just to ensure that if elimination does go forward, then I've got the proper setup. So if they do want me to give stereochemistry, that's one of the things I got to remember. Now, with that said, let's talk about what needs to happen here. CH3 and Br. So at first glance, you're going to look at this and say, hey, this has a Br, this has an OH, so this is going to be pretty easy. I just add a strong nucleophile in. This strong nucleophile is going to come in and it's going to substitute for that bromine, and that bromine is going to leave, right? Okay, well, if you do that and if you fall for that trap, that OH group is going to go right here. It's going to go at this carbon, not down here below. It's not going to work for you. I'm sorry, it's just not going to work. So there's more to it than at first glance. More to it than meets the eye. Are you an 80s child? If not, watch G.I. Joe cartoons and you'll know exactly what I'm saying. The problem here is that this carbon, when the bromine leaves, this carbon could end up forming a carbocation. We know we don't want the OH here. We know it can't go there. We are going to have to rely on that carbocation to shift. But it's not going to shift. It's tertiary. How can we get that carbocation to move down here so we can put an OH group? Well, just a normal substitution, elimination kind of thing is not going to, or substitution's not going to work for us. We're going to have to get a little bit more creative. So, I need to change the molecule up a little bit. I need the freedom to go in and change up this molecule so I can shift the carbocation. How do we do that? Well, I'm going to promote an elimination reaction to happen. And I'm going to bring in maybe a strong nucleophile. Doesn't matter what you want to pick. Let's just do OH. Strong nucleophile. And if I want elimination to happen, it normally happens anyway. But just to ensure it, let's put a little bit of heat onto it. So what happens is that this bromine will now leave. That bond leaves. That carbon forms there. And the nucleophile is going to come in and promote elimination, not substitution. So it goes to a neighbor carbon, which is down here. That carbon gives that OH a drink and says bye-bye, and a double bond forms at that location. Now, we're getting a little bit closer. Once I have this double bond, I can now play off of double bond reactions, can I? We need OH group on. Okay, so if the double bond breaks, two sites of attachment open up. Here and here. If I add something like water and acid, that will give me OH. That's what we're after. But that OH, folks, is going to go here because H plays with other hydrogens. Again, that's not where we want it. A typical substitution reaction would have put it there. Okay, so that's not going to work out for me. That's not where I want the OH. So you might go back and you said, well, we did talk about like mercury compounds and blah, blah, blah. Well, if you pick the mercury compounds, folks, it did the same thing. The double bond broke, two sides of attachment open up, hydrogen plays with other hydrogens, Markovnikov rules follow, and then on the other carbon, we get the OH group. That's not going to work either. We need this OH to go on in the backward spot. Oh, okay. All right, I know how to get OH to go on backward. I know how to add on OH in the anti-Markovnikov fashion. How do I do that? Oh, well, we take BH3 and THF, and then we add on a group of OH and H2O and H2O2 with that peroxide, and the double bond breaks. Two sides of attachment open up. Hydrogen plays with other hydrogens normally, but this time hydrogen goes onto the playground and says, ew, and it doesn't like it. And that hydrogen moves off to the other carbon. And then we add OH onto the other spot. Look at that. There you go, folks. That's how we do this. Again, it's cumulative. Again, it's a foundation process, and now you clearly see it more so than ever. Back from day one, you thought I was exaggerating. You probably thought, oh, well, he's just another instructor that says this kind of stuff because he wants me to pay attention. No, it's not really this way. This is cumulative. It is foundational. It is building upon a foundation more and more and more so. And you begin to crumble the foundation, you begin to crumble the organic material that you're learning. Now, let's take a look at the product side. The product looks like it has came in with some stereochemistry. A CH3 group pointed forward and this OH group pointed backward. But notice it really didn't give me anything like that on the reagent side of the house. The only thing that I said is that for elimination to go forward, if we're going to use it, and we did have to use it, then this bromine has to be on an axial position, which means that the bromine has to be pointed one way and the methyl group has to be pointed another way. So if we did a solid wedge here to say that methyl group is pointed toward me, that doesn't get touched in the reaction, and look, over here on the product side, well, it's still pointed toward me. It didn't get touched in the reaction. If we wanted to do that, bromine would have to be on the back side. Okay, well, the elimination reaction happens, and folks, it doesn't really matter stereochemistry-wise because it eliminates the chiral carbon, and we form a double bond. Then when the double bond breaks, the H and the OH go onto the molecule, and quite naturally, what goes on is that the groups will go opposite of each other. So that automatically is going to really put OH group on the back side of the ring because methyl is on the front side of the ring already. So a trans formation kind of has happened for us. So everything went smoothly stereochemistry-wise. But those are the steps for the synthesis product. All right, here's another. 1, 2, 3, 4. Butyl bromide. How can we get that to go to that product? I have a carbonyl, C double bond O, on the second carbon from the end. Let's think about this. C double bond O. Let's go back. Let's try to remember this C double bond O. Do you remember how that formed? Well, I think the only thing that we said back then was that a C double bond O is kind of a rearrangement of a molecule that was here before. And I think there was like an OH group here and a carbon had to have a double bond. And we called this an enol. So I can get the C double bond O to form, and it will form naturally if I can get an enol onto this thing. Well, that means that this carbon's going to have a double bond over here, right? So how can that happen? Well, how can I get a double bond into this thing? Oh, I start off with a halogen here. If I could maybe eliminate that halogen and force this carbon to create a double bond, and then if I could add on maybe an OH group onto this carbon, that will rearrange naturally to give me the C double bond. Oh, that's what we'll do with the synthesis problem. All right, so down here, let's start. CH2, 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 and Br. I need this thing to eliminate. All right, so I need elimination to be preferred. One, I choose a very strong base maybe, right? Something that can get in there and easily rip things out. So let's do like an OH group. There's a strong base. And then in addition to that, we also want to maybe encourage a little bit of heat. So that way this system will for sure go in and rip a hydrogen off to create a double bond. So in this scenario, we have this alkyl halide, and this OH group is going to come into the picture, and this carbon's going to say, hey, bromine, it's just not working. You got to go, so I'm tired of looking at your ugly face. And that carbon kicks the bromine off. Well, this buddy beside of carbon is going to say, oh no, OH, ping, off you go, because my friend is not ready for another relationship yet. So I'm going to make you leave him be, give him some time, and by the way, here's a drink. And here is a hydrogen now to form water. So that OH goes, okay, off it goes. So what we've done here now, CH3, CH2, CH2, CH2Br, what we've done is that we have eliminated the bromine, and then on the carbon next door, it's provided a drink to the friend, or to that incoming OH group that was up to no good, and then we create a double bond molecule. All right, so an elimination happens. It just so happened that we did something that persuaded an E2 reaction to happen. All right, so there we go. And now I need to eventually end up with this product. So at this point, I'm just going to add simple water and acid. That's all that it's going to take. And the reason is because I start with my starting reagent. There it is. I break the double bond. I open up two sites of attachment here and here. H plays with other H's. So there it goes, CH3. And then on the other carbon, I get an OH group. Okay, so that's what we do, right? And then that OH group is going to reform, and it's going to give me this wait a minute. That's kind of weird, isn't it? That's not going to work out for us. I don't have a double bond in order to shift. I was so close, but so far away. Okay, so there's got to be another way that we can get there, because if I form the double bond like I did here, and then I add water and acid to it, folks, this is not going to work out for me. So I'm going to have to erase that choice. That pathway leads me down a wrong direction. So that means I can't add water and I can't add acid here either. I got to do something else. What can I do? Well, if this is the case, I had to break a bond here in order to add the OH on it. So that means that this has to be a triple bond in the beginning, right? So I've just created a double bond. I need a triple bond. How am I going to do this? Kind of tricky, but watch this. Here, I'm going to add Br2 and DCM. What happens when I do that? The double bond breaks, and two sites of attachment open up. Okay. So double bond goes away. Two sites of attachment open up. One here, one there. Bromine goes on in that spot. bromine goes on in that spot. We just talked about these examples, didn't we? And now what needs to happen? I need to eliminate those halogens. I need to eliminate both. So I'm going to bring in OH, but I'm going to bring in 2 moles of this stuff. And I'm going to make sure that I heat it up as well, just so I can tell you that we are promoting elimination. Okay, so CH3, CH2, CH, and then this CH2, this has a bromine on it, this has a bromine on it. So when I undergo an elimination reaction, this bromine whoop, goes away, and a hydrogen over here goes away, and we form a double bond between the 2 buddies. Well, this one brought an ugly friend to the club too. We got 2 moles of elimination product, so bloop, goes away. This neighboring hydrogen goes away, and another bond forms in between the 2. And look, I've now created an alkyne. Now at this point, I can add on water with a little bit of acid. When I do that, I'm going to come up here, CH3, CH2, carbon, triple bond, CH. When I add water and acid at this step, I break the bond. 2 sites of attachment open up, here and here. Hydrogen plays with other hydrogens, so it goes to the right-hand side. The OH group shows up on the left-hand side, and now we get automatic ketal-enol rearrangement, where this enol group rearranges to the ketone group up here at the very top. Again, what looks somewhat simple, I can maybe pick out some pieces of the reaction scheme, might be a little bit more complicated when we do it from scratch. And here's one of those examples, folks. So I'm going to take butyl bromide, and I'm going to react it with hydroxide in the presence of heat to promote an elimination reaction. That's then going to form 1-butene. 1-butene is then going to react with bromine and methylene chloride, and an addition reaction is going to happen onto the double bond. That double bond will break, and bromines are added on to those neighboring carbons, forming a 1,2-dibromobutane. That 1,2-dibromobutane will then react with 2 moles of hydroxide in the presence of heat to promote 2 rounds of elimination to happen, forming an alkyne. And that alkyne is 1-butene. That 1-butene will then react with water and acid in an addition reaction, and water will add on to the triple bond to create, in a Markovnikov reaction, to create a 1,2, right? So this is a 2-butanol, but this is also a 1-ene. So 1-butane 2-ol structure. That then undergoes tautomerization, and that tautomerization will form and rearrange to give me this group, which is ethyl methyl ketone. Folks, that's a semester wrapped up there. That is a semester completely wrapped up into one problem. Here's another example. This example I'm showing you, but we're not really going to do them. I do want you to keep in mind, though, molecules can play with themselves, right? That's okay. Nobody's going to scream at it. Nobody's going to get mad. It's natural if it's going to happen. And this molecule can react with itself in order to form this ring. Look at this. This is 1, 2, 3, 4, 5 carbons in total. 1, 2, 3, 4, 5 carbons in total. We have a double bond that's here. We have a halogen that's here. This thing can kind of wrap around on itself if it has the right circumstances. But I've left off these types of reactions. I just don't think that we need to deal with that in the first set of organic lectures in the first semester. So this is just a reminder that not everything that we do has to involve another reagent. This molecule can react with itself in order to give us this product that we see over here on the right. We're just not going to see a lot of those examples. All right, so this one we're not doing. You won't see on a test. You won't see on Blackboard. You won't see on any other assignment that I send out. Nothing at all. Another thing I want you to take away before we end this lecture series: bulky bases favor elimination over substitution as well. Bulky bases, here's this negative, right? And this is on a tertiary carbon. That is what we call a bulky base. Here we have an oxygen that's negative, but it's not on a tertiary carbon. So these bulky bases just have a really hard time getting in here and substituting for that bromo group or whatever the case is. So whenever we see bulky bases like this, elimination is going to be preferred. And whenever we see this non-bulky base, this negative that's not really restrictive, that can actually go in here and kick out that bromine, then we do see a substitution happen at a higher rate and at a higher level. Here's another kind of summary chart that maybe you can write down. It might help you when the tests are concerned and the assignments are concerned. And this really ranks the carbocations up at the top. So here you're seeing primary, secondary, tertiary, or the halogens up at the top, and the nucleophile or base strength. All right, so strong, weak, all the way down. We didn't really do a lot with the methyl groups. I'm going to actually write out that column completely. We focused on primary, secondary, tertiary alkyl halides. And notice here, strong promotes elimination most of the time, except for the fact of a primary. They're a little tricky. Here we have strong. Well, here we've got a scenario, though, that gives me substitutions for primary, secondaries, nothing for tertiaries, because of what we call the base strength. Then we have a set of weaks that are down here. Weaks will always kind of go elimination routes when they can. And then weak and weak, well, no reaction actually happening here on primaries. SN1E1s, SN1E1 combos. So this is just kind of a summary. It might be actually confusing for you, and if it is, don't write it down. But what they're doing is that they're looking at nucleophiles, and they're looking at base strengths, and they're pairing them up in a different way. So I know what you're going to say. You're going to look at this and say, wait a minute, this is a weak nucleophile. And you told me weak nucleophiles will always give me SN1E1s. But here we're seeing E2s. That's right, because they're looking at base strength. And this is a very strong base. And what's the definition of a base? So that's why this chart looks a little bit different than what we've had before in the past. So if this confuses you, folks, don't even write it down. Just use the rules that we've talked about so far in order to get to this point. And finally, here's another flow chart. Another flow chart that says if you have a primary alkyl halide, you can get SN2 or E2 to happen. That carbon's got to be a cheater. There's no friends to protect it. There's no friends for comfort. So if it's a strong nucleophile, or if it's a strong nucleophile with a strong bulky base, that gives you an idea of which route would be preferred. The same thing with secondaries. Secondaries are going to split off, and they can give you E2s and SN2s and SN1s and E1s. We talked about that. The way we determine the difference, if I pick something strong, it goes SN2 E2 route. If I pick something weak, it goes SN1 E1 route. Well, when I pick a strong nucleophile, it's not elimination only. I mean, the preferred way is to go elimination, like we've said. So if I use a strong base like OH or OR, then I can ensure an elimination is going to happen. Or heat, which is what they leave off on this flowchart. If I do a strong nucleophile, but I pick out something that's maybe a weak base, so this would be like I-. I see the minus there. It's strong, but it's not a strong base. Or CH3CO2. I can promote a substitution reaction happening. And then tertiary over here are going to be broken down again. Tertiaries, strong bases, elimination is going to happen. Weak bases and weak nucleophiles, substitution and elimination can happen, but that carbon's going to be a non-cheater. It only sees one thing at one time. All right, folks, so those charts might help. Those charts might be confusing. I don't really know what to tell you. If you don't like them, don't write them down, don't study them, and use my notes instead. And that finishes up the elimination reactions of alkyl halides. And that also finishes up the organic chemistry class. Yay! A round of applause, everybody. We're finished. So we have went on this really long journey together. We've started off talking about a review of Gen Chem. Then we migrated into acid-base theory, which is where you can find some of that information about strong and weak bases. And then we talked about the reactions of alkenes and the reactions of alkynes. We talked about the nomenclature of alkanes, alkenes, alkynes. We talked about substitution. We talked about elimination. We talked about 3D orientation, stereochemistry of molecules, and delocalization, which was movement of electrons through a molecule. There was quite a bit that we've done in this set of 10 lecture modules. So folks, good luck. Good luck on the assignments with elimination. Good luck on the upcoming tests for substitution and elimination. And more importantly, good luck studying for the final exam. You're seeing that this information really blends extremely well from day one all the way to now. So with that said, my job is now complete. Except for grading your tests and your exams and your labs and everything else that's going to be coming my way. But my job for lecture is now complete. So I hope you've learned something. I hope that you've learned a little bit, at least, of organic chemistry. I hope that you can take away some of this stuff. I hope that you feel a little bit more comfortable in an organic class. Maybe sometimes I get people that have taken organic before and they flunked out of it the first time. And then they take this one and they're like, what was so bad about it? What didn't I understand? Well, that's probably because they didn't break the double bonds on you. That's probably because they didn't talk about anti-Makovnikov and the hydrogens going ew and going away. It's probably because they didn't talk about exceptional nucleophiles, Mr. and Mrs. Americas coming in and the carbon buddy slapping it and saying, off you go, here's the drink. It's probably because they didn't use sound effects. I think that's why. That's why you didn't enjoy organic chemistry the first time if you've taken it before. So whichever route that you decided to end up with me, I'm glad that you sat in through these lectures. I hope that you've learned something about organic throughout these lectures. And if I just did my job in the first lecture module and you felt more comfortable about general chemistry now than ever before, and you didn't learn anything about organic chemistry at all, maybe your grade's going to show it, but I've at least did my job in a way. I let you understand chemistry in a different perspective. And that's what I'm here and that's what I'm all about. All right, so if you have to contact me, folks, you know how to get a hold of me. The other thing that I also want to share with you is our chemical technology program. I'm going to make a selfish plug here. And the ChemTech program is a program, it's a 2-year program at Cape Fear. And we require general chemistry and organic chemistry in our program. So the chemical technology program puts you to work in a laboratory, pharmaceutical, environmental, forensics, cosmetic, food and beverage, chemical engineering, research and development, quality control, you name it. If it has a laboratory space, then our graduates can work at those spaces. And then our graduates do transfer on and they get things like bachelor's of chemistry degrees and so forth. If you're interested in it, we would love to have you in a program. The chemical technology program can be found on the Cape Fear Community College website. As you go down, you're going to see a couple of different links. One is our AAS degree, And when you click on that link, it will show you the requirements that we have for our program. So you can go through and quickly check off these things and see if you have the electives or not with it. But yet again, if you're already in Organic 1, then that means you have Chem 151, 152, 251 now under your belt with one more organic class. So you're already kind of enrolled in our program, believe it or not. And then we also have a version, Chemical Technology CCP, for high school students. So if you're a current high school student, you're interested in our program, you're interested in taking more classes with me or with us, then this is a way that you can get your foot in the door with us and maybe complete some classes before you graduate from high school. The other thing that's not listed here is a Chemical Technology certificate. So this certificate is not an Associates of Applied Science. It's just a couple of courses that you can take with our program. You'll get a certificate when you complete those courses, and you can put that kind of thing on a resume because some laboratory environments, believe it or not, are okay with a thing like a certificate and not a full-blown associate's or bachelor's degree. So if you would like to know more information about our program, you can find us on the CFCC webpage, website. The other thing, please tell other people about our program. We are a floater program, which means that we float around. Only a certain group of people know about us, and we would love to be able to offer multiple classes throughout the day because our enrollment has skyrocketed throughout the day. We cap off at 14 students. We don't really get any more than that. And after those 14 students, after your first year, those 14 students basically do all laboratory coursework, all on our equipment, all on the advanced analytical instrumentation that you would see in a laboratory environment, gas chromatography, mass spectroscopy, ICP, AA, IC, you name it, we have it in our lab facility. So if you or someone you know would benefit from our program, please send me an email. Let me know. I would love to talk to you. I would love to show you around our lab spaces. And until then, I wish you luck in whatever you decide to do. So if you have to take part 2, I hope to see you then. If you do not have to take part 2 of Organic, folks, please stay in touch with me. Let me know where you've ended up, what you're doing, what this course has led into as far as opening pathways and stuff up for you. I love to stay in contact with you if I can. So don't ever lose touch, and I wish you the best of luck. So I hope you have enjoyed your time with Organic, and until then, over and out.